We are.
Hello, everyone.
All right, you're welcome to class. Okay, so this is a continuation of our journey in Maths 202 exercise or solutions to exercises. Okay, so recall that we had moved from question 1 through question 7 or 6 rather, and this first module has about 8 questions, so we have 7 and 8 to look at. Okay, be right back.
You know, in this life, do what makes you happy.
Okay. When I name a video, use earpiece, I beg. Oh, Chief Gabriel can now. All right. Okay. So welcome back. So we had that short break to allow time for some of us to join. Okay. So and we are going to start now. Right. So recall that, like I said, we are starting from problem 7. Okay, so let's see. 7 says, with a very good example, agree or disagree with each of the following. Okay, so in other words, we are going to use example to show whether we agree or we do not agree. Okay, so let me put just agree or disagree with example in the following. Okay, so the first one says every first order equation is linear. Okay, of course this is not true. All right, first of all, when it comes to types of differential equations, we have different classes or classifications. Okay, so first is that differential equations are classified according to order. Okay, and what is the order of a differential equation? That is the highest derivative present in that differential equation. So we have order 1, order 2, order 3. So if I have something like y prime plus y equal to 0, this is a first order because the number of the highest derivative here is just 1. Okay, so it's first order. So if I have something like y prime prime plus, let's say, 2y prime minus y equal to 0, this is of order 2 because the highest derivative present is 2. The number of primes show the number of highest derivative present. Okay, so away from order, we now have what we call degree. Okay, so the degree of a differential equation shows the power of the highest derivative present. Okay, so for instance, here we have that the highest derivative present is y prime and the power is 1, and the same applies here. So in other words if I have something like y prime prime raised to the power of 2, then minus, let's say, 2y prime, then maybe plus 3y equal to 0. Okay, this is a differential equation of order 2 and degree 2. Okay, so for this one it is order 1 degree 1. This is order 2 degree 1, but this one is order 2 degree 2. Okay, so and the third classification of differential equations we have is what we call linear and non-linear. Okay, differential equation can be classified according to its linearity. Okay, so and there we have linear and non-linear differential equations. Okay, so an equation is linear if it satisfies some conditions, and the same applies to the non-linear differential equations. Alright, so for an equation to be linear, there are certain conditions to be met. So, and then if any of those conditions is failed or is not met by a differential equation, so then that differential equation is non-linear. Alright, so let me state some of the conditions for linearity. Alright, first is that the degree, or let me put it this way, the highest power of y and, or you can say, or its derivative, any of them, must be 1. Okay, so if I have any differential equation where the power of the derivatives of y or y is not 1, then that differential equation is non-linear. So if you check the examples I gave earlier, for instance, y prime plus y equal to 0, so this is linear because the power of these are all 1. Okay, so remember we said it has to meet the other conditions. However, this one met the other conditions I want to mention. Okay, so number 2, y must okay, let me put it this way. Y or its function must not multiply y derivative. Let's put it that way. Must not multiply y derivative. So if you have an equation where, say, you have something like say y prime plus or let me say y prime prime plus y prime, maybe minus 2y equal to 0. So you can see that this is not linear because there is a product of y and a derivative of y. Okay, or let's assume you have something like 2y here. Okay, so 2y now is a function of y multiplying y prime. So once that happens, then it fails the condition for linearity. Okay, the next one, y or its derivative must not be the argument of a transcendental function. Okay, so recall that transcendental functions are functions of trig, exponents, and logarithms. Okay, so your y or its argument, y or its derivative must not be an argument of any of these in a differential equation. If that happens, then it is not linear. So for instance, I have something like y prime plus cos y equal to 0. Okay, so this is first order differential equation because you can see that the highest derivative present is 1. Now, is it what is the degree? Of course, the degree is 1. You can also say that the degree is undefined because you would need to clear this transcendental function on y to be able to determine the degree of that. But you can actually say maybe 1. And now, is it linear? Straight away, it is not, because y is an argument of cosine here, So you say that it fails the condition, one of the conditions for linearity. Okay, I think these three are okay. I think these three conditions are enough, to determine the linearity of a differential equation. However, in the case of the power the power of y or its derivative, if it is a fraction, then you need to clear that fraction before you are able to determine the degree, in terms of even types where we talked about degree. Okay, so you need to clear any fractional power to determine whether the derivative or the differential equation is of degree 1, 2, 3 or whatever. So okay, quickly let's now look at the question we have. Okay, so for number 7, okay, so let's start. So the first one says every first order equation is linear, and the claim here is disagree. Okay, so we disagree with this because it is possible to have a first order differential equation that is not linear. And let me not even use 2 here. If I have y squared equal to 1, this is a beautiful example of such differential equation. Okay, so this is first order, and then there is the power of 2. I can actually write something like this: y prime raised to the power of 2 plus y equal to 0. This is also a first order differential equation, but it is non-linear. All right, the second one, B. Okay, so the second one says that every homogeneous equation is autonomous. All right, the verdict here is disagree as well. So we disagree. And what then is a homogeneous equation? Okay, so and can we give an example of the one that fails this? Okay, so we are saying that not all homogeneous equations are autonomous. Meanwhile, autonomous means that the equation has only y as the variable. That's in terms of implicitly or explicitly. Okay, so for instance, if I have like something like this is a clear example of an autonomous equation, because you can see only y as a variable present here. Okay, so now when we have something like y prime equal to y over x, is it homogeneous? Okay, first of all, to define a homogeneous equation is that if you have your y prime or whatever, whether prime, of course, we can write this in this form. Okay, so whether it's prime or prime or whatever, so if it is prime, I can write it as y bracket 2 up there. If it is only prime, I can write it as y bracket 1 up. Okay, so depending. Okay, so let's assume I have nth derivative of y to be equal to this. So we define it to be homogeneous if okay, how do I put it now? Okay, so if I have, let's take it that I can write this in this form, maybe k y all over, let's say kx, okay, in such a way that you are able to bring out your k from the both of them. Maybe whatever be the value of your k can come out maybe as power n, and then below is also as power n. So you are able to factorize out your k, whether it's a product or a quotient like this, okay, and your x and y will still remain. So you declare that it is homogeneous, okay. And so this actually gives us a beautiful example of a homogeneous equation that is non-autonomous. Remember, you can write this as x y prime minus y equal to 0. Okay, so remember I transferred this over here and then multiplied through by x, and then I obtained this. So here you can clearly see that there is a variable x, so which denies autonomy for this. So however, it is yet a homogeneous equation. Okay, so that means not all homogeneous equations are autonomous. Okay, so let's look at the next one, the third statement. Every differential equation has constant solution. Okay, so every differential equation has constant solution. Okay, so what's the verdict on this? Is it possible? So you can see that this is not true. All right, so it's also disagree. We do not agree. Okay, so what do we mean by constant solution? If I have something like y prime plus y equal to 0, yes, of course, this equation has a constant solution, because if I make my y to be equal to say 0, you know 0 is a constant, so you see that if you substitute y as 0 into this equation, it will be a solution. Okay, yes, it will. All right, so let me just use that. That's a trivial solution as an example. However, there are some equations you can write and a constant solution will not work. Okay, so for instance, if I have y prime equal to x, okay, so you discover that there is no constant solution for this. Okay, so even if we make our y to be 0, so you discover that if our x is not 0, then of course this is not going to be a constant solution. All right, so yeah, you cannot have a constant solution for this if x is not 0. All right, so we disagree. You can have a differential equation. Of course, you can write this as y prime minus x equal to 0, and this is a very beautiful differential equation, and it has no constant solution. In fact, you can talk about this one, y prime minus 2x equal to 0. In fact, the solution of this is something of this nature, y equal to x squared. Of course, you can have, let me say, instead of x squared, you can just have something like ax squared, where in fact plus b, where a and b are constants. Of course, any of this will form a solution for this guy. All right, so of course you are going to see as we continue how to check whether a function is a solution. Is that if you substitute it here, you should get 0. Okay, so of course from here, if I differentiate this, I'm going to get okay, sorry, here there shouldn't be a here, so it should just be x squared plus b. Okay, so or x squared plus a. All right, where that b is a constant. So this will definitely give you 2x, and of course if you differentiate your b here, you get 0, and by the time you substitute here, you will get 2x minus 2x, which is 0. Okay, so that means this is the only family of solutions for this, and so there is no constant solution as well. So it is not all differential equations that have constant solution. All right, that is the third one. All right, and there are others which I'm going to allow you to attempt to respond. They are easy ones as well. Every initial value problem has a solution, and it's no, because in fact, look at this. Where is it? That is D. Am I sure? Okay, yeah. All right. So it says, the statement says every IVP, initial value problem, has a solution. And of course this is a straight no, because when we are looking at IVPs, we also study the concept of the Picard's theorem, and the Picard's theorem is the theorem that we use to determine whether a particular initial value problem has a solution, and if it does, is the solution unique. Okay, so if there is a theorem that tells whether a differential equation or an initial value problem has a solution, it then means that there is a possibility of no solution. So if it fails that theorem there, it gives you no solution. And in fact, this is a perfect example. An example here is y prime equal to 1 over y, where our y of 0 is equal to 0. Okay, so remember, an initial value problem is where we give initial values to x and y, and then for this case here, what this statement actually means is that when x is 0, let my y be 0. Okay, that's actually what this statement means. All right, so here you discover that there is no solution for this, because if we even make a substitution here straight away, you will discover that your y cannot be 0, because y here is a denominator of 1, and if it becomes 0, then it is undefined. Okay, so there's no solution for that IVP. Okay, so the fifth one there says every first order equation has a singular solution. Okay, this is also a disagreement. All right, a singular solution is a solution okay, so a singular solution is a solution that is not obtainable from the general solution. Okay, so and there are some first order differential equations that do not have singular solution. In fact, there are many of them. I said I wanted to leave these ones for you, but I'm ending up answering all of them. So it says every first order differential equation has a singular solution, and I've tried to explain what is a singular solution. That's a solution that you cannot generate from the singular solution. For instance, in fact, the simplest way to see it is look at this. If I have y prime equal to y, okay, so we can try to solve this equation, and if we solve it, we are going to get our y to be equal to cex. Okay, don't worry, we are going to see how to solve differential equations. And from here, in fact, even looking at this point, you would see that every other equation here actually can is actually gotten from this particular what do you call it, this particular solution, all right, by giving values to c. Okay, so if I give c, like now the constant solution here is actually 0, y equal to 0, and most times our singular solutions are usually constant solutions. Remember I said most times, that means not all the time. So it's possible to have a non-constant solution as a singular solution. Okay, so but in most cases, but now this is the only possible constant solution here, and then we can clearly see that it can be generated from here by making our c to be 0. So you can clearly get that y is 0. So you can see that all these possible solutions of our differential equation y prime equal to y is actually from the general solution. Okay, so it means that it is not compulsory that every first order differential equation must have a singular solution. And then number 8, which is the sixth one, which is f and g, I'm going to finally leave for you, but I'll read it. It says there's no differential equation that possesses only the trivial solution. So disagree or agree. Remember, this one is disagree. Okay, then every autonomous first order has its standard form as this: f of x, y prime to be equal to 0. Every autonomous first order has the standard form. Remember, I just defined an autonomous differential equation. Of course, the explicit presence of x denies the fact that it's autonomous. So I've already answered this one. This one is disagree. So it's not true. If it is autonomous, then x must not be in the standard form. It should rather be something of this nature: f of y, y prime, and then should be equal to 0. That's for a first order. Okay, and that's the end of problem 7. So we'll quickly look at problem 8 after this short break. Finish it. It's my need.
I'm trying to do.
To avoid quarrel. See what? Okay, so welcome back. So for problem 8, okay, so like I said, which is the last one for module 1. For module 1, we are to solve a problem, and the problem is to derive the equation from a particular, that's to derive the differential equation from a particular equation given to us. Okay, so let's look at it. It says that they even started by saying by taking two derivatives, eliminate a and all of those. So, but that's just to tell you how to do it. But see what they are asking you to do to form the differential equation from the equation. So from this equation, you are given x is equal to a cosine of pt minus beta. All right. So now they said we should eliminate a and beta, meaning that a and beta are the arbitrary constants here. Okay, so normally in forming a differential equation from a primitive equation that is given just as this one, your job only is to eliminate the arbitrary constants. So depending on the number of arbitrary constants, that will tell the number of derivatives you will perform to be able to get what you want. But here they said by taking two derivatives, which actually aligns with what I just said. So you have two arbitrary constants they want you to eliminate, and that's why they told you to take two derivatives. Okay, so let's go. However, they actually have started by taking the two derivatives for us, which is not a big deal. The derivative of x with respect to t. So our t now is the independent variable here, while x is the dependent variable. So here we have minus p times a sine of pt minus beta. All right. So this is actually what you get, because when you differentiate, the constant will be here. So when you differentiate cos, you get minus sine. Then you bring down the whole of this and then differentiate this and use it to multiply. So of course, if you differentiate this with respect to t, you will get p. So remember, you got minus. So that minus sine times a will give you minus a sine this. Now, by the time you differentiate this, you get p. Use it to multiply. You will now get this other p that is here. Okay. So in going for the second one, that's, let me use this. That's in going for d squared x dt squared. What are we going to have? That means we want to differentiate. We want to differentiate this again. All right, so to do that, we are going to get, remember, the derivative of sine is plus cos, so this is going to be remaining as negative minus p. Then cosine, you bring down this the way it is, which is pt minus beta. Then you multiply by the derivative of this, and the derivative of this we said is p, so that means this p is going to carry a square. All right, and that's exactly what they have here, minus p squared a cos pt minus beta. All right, so now that's the two equations we have, 1 and 2, and we are asked to now complete this to eliminate those two constants. So we are to eliminate a and then beta from the two equations, and then use it to generate a differential equation. Okay, so let's try. All right, first of all, actually this one now is equation 2 and 3. The first one that was given should be the equation 1. Okay, so this is actually the equation 1. Okay, so let me try to reduce this to allow us see this as we try to handle it. Okay, so let's go. So what do we do now? From what we are given, if we substitute from equation 1, if we substitute, watch what we have here. You can see that our equation 1 can actually go into equation 3. Okay, so equation 1 is a cos pt minus b, and I have it here. So I can actually substitute, let me use put equation 1 into 3. Okay, if I do that, I'm going to get d squared x all over dt squared is equal to minus p squared. So the whole of this now is my the left hand side is equal to x, so I can replace here with x. Okay, and of course, have I been able to eliminate? Yes. Is there any other constant? Remember, we are told to eliminate a and b, and you can see there is no more a and b here. Okay, so, and you are done. It makes the whole work is done. All right, so assuming this was in y, I can write it as y prime prime is equal to minus p squared y. Okay, but since it's in x, I can actually also still put it in that form. That will be x prime prime is equal to minus p squared x. Okay, so because the double derivatives means prime prime, and then I can actually move it a little bit further by transferring this to the other side, and that will give me plus p squared x equal to 0 as the differential equation required. Okay, so and that's a very good place to stop. Okay, all right, so that's exactly what we are asked to achieve in that exercise 8. That's to generate the differential equation from that primitive equation given here. All right, so and that's the end of module 1. Okay, so which we started in part 1 and we did part 2, and this is part 3. So we needed 3 parts or 3 sections to finish up our module 1. Okay, so and we are going to end it here. Module 2 will be in a fresh section, and that we will start in a short while after a brief break. So see you. Please kindly give a thumbs up to the video, make a comment at the end of it, and we will see you in our other videos. Bye.